This box contains an MMIC, an SPF-5043. As in the previous video, I have 19 dB in front of it, but also 12 dB on the output side, because this has a lot of gain. And the attenuator I have directly on the output of the oscillator. Here I had to insert 10 dB more gain to not saturate this amplifier. I connect the spectrum analyzer here, where I previously had the amplifier, and the power level here is minus 15.7 dBm. Above that I run into saturation with this amplifier. So minus 15.7 is the carrier level. This is the SDR IP. The carrier on 10 MHz. I have calibrated it to show 0 on the S-meter graph here, as you can see. And then I click on the reference signal I have placed here. It's this generator, 10 kHz below. And the S-meter here, it shows minus 50. Means I have set the level of the generator to be 50 decibels below the carrier. And then I want, of course, lean rod to show also minus 50 dB for that signal. But I have to make sure balancing is better. It has drifted a little bit. So here is the output from the Perseus, and I have set it to show minus 50. So it means that this scale now is decibels with respect to the carrier. And the bandwidth is now 1 kHz. So I switch off this extra signal. And here is the noise floor at a separation of 10 kHz. And it is minus 107, means 137.4 dBc per hertz. Quite horrible at 10 kHz. This is a frequency separation of 100 Hz in a bandwidth of 10 Hz. And then I see minus 99.5. This is a frequency separation of 100 Hz in a bandwidth of 10 Hz. And then I see minus 99.5. And this is 30 Hz separation in a 10 Hz bandwidth. And the level is minus 92.3. So here is the result for the SPF-5043. It seems this point, which is 300 Hz bandwidth, I must have made a mistake. It seems also that this is not quite a straight line, it's bending a little bit. And then the flat floor, as determined from the noise figure, is fairly high, because the signal level has to be fairly low. I am running this test at minus 15 dBm. So the floor is 15 decibels higher than what I found for the AMC 147, if I remember the label on the unit properly. I have unbalanced the amplitude by 0.1 dB, which is quite a lot. And now I'm running Linrad in coherent 2 mode, sending I and Q with respect to this carrier to the network to analyze in a second instance of Linrad. I'm setting the phase control. If I turn it around, you can see here. So this is the point where the signal has its minimum. It means that the carrier I have here is in phase with the two carriers in the interferometer. So I go for the other screen, and here we have, and you can see the in phase means amplitude noise is much stronger than the red track, the FM noise. And of course this is very sensitive to the precise tuning of the phase. So I change the phase a little in one direction. So something like this is where the discrimination is biggest. And looking here, while I turn from this point, well, you cannot even see it. It's the fine turning step. So this MMIC, it is intended for weak signals on microwaves. I have experienced before on 2 meters that it is the seriously limiting factor when it is used in a transverter, the E3DDK transverter. You can find videos about that if you look carefully. This is just very different from the AMC147 that I studied in the previous video.